Hello. What we're going to be talking today is about Astro Tools. These are going to be instruments that astronomers use to actually look at things that we can't see with our eyes. You guys have all probably looked up and you've seen stars. You may have seen the Andromeda Galaxy, but astronomers actually want to see these things much more clear, and they want to see things that are much farther away. So these tools are going to be designed to allow astronomers to do the best job they can doing what they do best. This is the Keck, I think the Keck Observatory up on top of the big island of Hawaii. We're going to find out sooner or later that telescopes are really good to be put way up in our atmosphere, far away from cities. Not exactly sure if that's supposed to be a city in the background, but you can see this is way far up. Cloud cover would be, a majority of the cloud cover would be below this. But this is a reflecting telescope. The bottom of this can that you see here, probably 17-18 feet across, is a concave mirror. Light would go in, hit the mirror, bounce up, hit another mirror, and then bounce back down to a collector, usually a CCD, a charged coupling device camera, which would record the information, store it on a hard drive so it can be viewed later. Or you could sit in front of it looking through the eyepiece, looking at whatever this telescope sees. And what it basically wants to do is to make the iris of your eye the size of the opening of the telescope. This is a refracting telescope. A refracting telescope refracts or bends light. It does so with a glass or a plastic lens. This lens takes in parallel light. If you put your eye back here, you're going to receive very little of what goes in here, but the job of this, the objective of this lens, is to bend the light. And you can see that it actually gets closer and closer and closer and closer. It gets to this point, and there's probably another lens in there, which is actually going to be a concave lens, which would bend the light back parallel. Hits another convex lens, bends it, and you'd put your eye right there, or you'd put the recording device right there, and it would see basically what goes inside this telescope is all the light that would hit you in the eye. This is why if you've ever looked at the moon through a telescope or a pair of binoculars, it looks much brighter, maybe to the point where it makes you squint, because you're not used to collecting that much light from the moon, which is normally very easy to see with your naked eye, and why you never ever want to point one of these things, any kind of a lens, which is going to concentrate light toward the sun. This is a reflecting telescope. Instead of having something at the front as the objective, its objective, or the primary job of this telescope, is to use this concave mirror. Again, taking in the parallel light. With this concave, it bends it in, hits a secondary mirror. You wouldn't want to put your eye right there because you'd be blocking all this sunlight. The light actually still even comes here and bounces up, and comes there and bounces up, so it collects a very large amount of solar radiation. Or stellar radiation. Hits a secondary mirror, which straightens it back out, hits another mirror, straightens it back out, hits another mirror, keeps it straight, and you'd put your eyepiece right here. A lot of people think telescopes are to magnify. Their job is to collect as much solar radiation or stellar radiation as possible. You can put a magnifier at the eyepiece to magnify the image, to make small stars look larger, to make craters of the moon more visible, but the real job of a telescope is just to collect the light. This is a radio telescope. These two are what are called optical. This is a non-optical telescope. The basic idea of a radio telescope is the same as this reflecting. It has a material back here, could be as simple as chicken wire, but it takes radio waves, which are invisible to our eyes, takes non-optical radio waves, and does the same sort of thing. Collects them, bounces them up to an area where they can be collected, and then a wire would bring it down to a house, or beam it through the radio waves to some other location where it can be stored and viewed whenever possible. These are the electromagnetic radiation, or the electromagnetic spectrum that telescopes are designed to collect. These two only collect this very small amount visible. This radio telescope can collect these much larger waves. We can make X-rays for infrared, ultraviolet X, and gamma ray as well. This picture shows you that these waves all have two things in common. They all travel through space as waves. These waves, like visible light, travel at the speed of light, 186,000 miles per second. It also shows you that these waves differ. They differ in what's called wavelength, or the number of crests and troughs you see in a certain area. If these were traveling toward you, you'd see these would hit you very, very, very fast. These would hit you slower, and these would hit you the slowest of all. High energy waves, lower energy waves. The numbers you see here, I think, are in centimeters. So that would be 1,000 centimeters. This is 1/100th of a centimeter. This is 1/1,000,000th of a centimeter. This is 1/4,000,000,000th of a centimeter. Maybe 1/1,000,000,000th of a centimeter. 6, 9, 12, 1/1,000,000,000th of a centimeter. So you're taking a centimeter, which is very small, cutting it up into a trillion pieces. Excuse me. This is a glass prism taking white light. It bends the light into the individual colors, the Roy G. Biv, splits the white light into the colors that actually create white light. Your clothes do something similar to this. Red clothes will bounce back red light, absorbing everything else. Blue clothes bounce back blue light, absorbing all the rest. But this is the continuous spectrum. You can see spectra down here of stars. That's stellar spectra. And it's showing you the colors of the visible spectrum, Roy G. Biv, sort of written backward. It also shows you these darker lines that are inside. We can use these lines to determine a couple things about stars. If we actually know what lines for known elements here on Earth, like hydrogen, helium, argon, gold, platinum, magnesium, we can actually look at the starlight and actually see lines in the same location and actually know those elements are located in stars. If you take a look at these three stars, you can see a couple of them are similar. Those top two look fairly similar. This bottom one's got lines that aren't visible in the other two. This is showing you something called the Doppler effect, which is an apparent change in wavelength of light and or sound. You may have actually heard it with a police car, fire truck, train, something that's coming toward you or away from you. It changes pitch. Light does the same thing. We have four stars located in actually one star located in four different locations. When it's located in position 1, it sends out a wave, and this wave goes out in all directions, signified by this number 1. If you notice, that is in the middle of this circle number 1. As this star starts to move, it actually sends out another wave. If you look at position 2 and circle number 2, it's still in the center. You look at position number 3 and circle 3, still in the center. 4 and circle 4, it's still in the center. It's still sending out waves at the same wavelength. But now that it's moving, what happens is, as it moves toward an individual, these waves get clumped together, and what you get is a higher frequency wave, more like this. And again, if you look at infrared and ultraviolet and visible, this is the red end by the infrared, which is more red than red, and this is the violet end, Roy G. Biv, more violet than what we can see with our eyes, more red than we can see. This is even more violet and even more red. Gets more red going this way, more violet getting this way. The only light we can see is there. So this is a star producing some form of electromagnetic radiation that looks like it gets jumbled together. It gets shifted towards the violet end. We're going to call it a blue shift. And the observer who it's moving away from, you can see these waves get pulled out. They get spread to a much lower frequency, more like this. Gets shifted more towards the red end. That's called the Doppler effect, an apparent change of wavelength due to motion, whether it be moving toward or away. If this was moving actually toward us, we wouldn't be able to see, or if it's moving laterally to us, you wouldn't be able to tell the difference in wavelength. It's like if a police car was running and you were in a bicycle or a motorcycle going at the same speed, that siren would sound the same all the way. It would only sound different as if you pulled away from it, where it actually gets spread out, or if you let it actually approach you, where it gets crunched together. These are the three types of spectra. We're going to talk about them a little bit later, but continuous spectra, continuous color all the way across. Emission spectra, usually a darker background with brighter lines. Emission, basically meaning that it's giving off the energy, but it gets passed through something else. And absorption, it is when we actually get a colored background in dark lines, and this is where we actually get something a little different, and I'll explain that when we get to the right slide. SWBAT's what I want you guys to be able to do when we get done with this particular slideshow. I want you to know what the function of a telescope, whether it be optical or non-optical. I want you to know the function of a telescope. I'd like you to know the difference between optical telescopes and non-optical telescopes. Optical telescopes have the best location possible. We'll talk about that. What are the name of any kind of a telescope that uses a lens or a mirror to actually gather light? And if you think about it, mirrors reflect light, and lenses refract the light. So that's going to actually deal with two different types of telescopes. One of them called a refractor, the other one called the reflector. Both of them actually gathering visible part of starlight. What advantage does the Hubble Space Telescope, which is actually being replaced, I think, in 2 years, 2015, with the Webb Space Telescope? It's a larger telescope. It's going to actually see things clear, but I really wish we'd keep the Hubble up there too, because it actually sees much better than what we can see from down here on Earth, which is the advantage. What are some of the forms of, and actually all of the forms of electromagnetic radiation that can be seen and not seen? What do the electromagnetic radiation, how do they differ in terms of wavelength and speed or whatever? How do radio telescopes work? And all these we sort of talked about on that initial screen. How do separate light sources, actually how are they affected when they pass through a prism? What can astronomers learn when they actually look at the spectra of stars? What are the three types of spectra? How are elements identified in the spectra of stars? How does the spectra of a star give us the characteristics of that star? What is the Doppler effect? What's a redshift? And what is a blue shift? Okay, what are the functions of telescopes? Lots of people think that telescope is for magnifying, but the real job of a telescope is to collect and then focus light. Again, a telescope wants to collect enough radiation so you can focus it in on your eye, so you can actually act as though that eye is as big as that telescope. It does so with an objective lens, or it does so with an objective mirror. It does it with an objective, which is the collecting that information, collecting as much of that electromagnetic radiation as possible, and then you need to focus it so we can make sense. Light energy, called the electromagnetic spectrum or the EMS, and again, the only part we can see with our eyes is visible light, Roy G. Biv. Here's the electromagnetic radiation again. We actually have the wavelength. We can see radio waves are kilometer in size. We get down to microwave, they're down to centimeters. We get down to X-rays, they're down to like a billionth of a centimeter. And we can even get smaller, trillionths, quadrillionths of a centimeter, way down with X-rays. Notice how close these guys are packed together, and they get farther and farther and farther and farther and farther apart as we move to the low end. These don't pack as much energy. These pack a bunch of energy. These are created by relatively cool bodies. These are created by incredibly hot bodies. Our sun does a really good job of producing the light in this area. We do have stars that produce more in this area, and we have stars that produce more in these. These, if it only produces radio waves, we cannot see them with our eyes. Just like if it only produces X-rays, we can't see them. But we do have telescopes that collect each one of these different areas of the electromagnetic spectrum. We do have optical and we have non-optical. We have telescopes that do both. They collect the radiation, they focus the radiation. For us to actually be able to see a gamma ray image, we have to transform that information to a visible form. So we're not really seeing how gamma rays appear, we're seeing how gamma rays appear optically. Okay, so we got electromagnetic radiation, talking about each one of these. We have the spectra going from one end to the other, and we have collectors that will actually do all of this. Secondary function of a telescope, you can put a magnifier on there if you want to. This will be done by the eyepiece, where you can actually switch out like a 10 to 100 to a 10th magnifier depending on what you want to do. If you want to focus in on craters, you probably want to increase the magnification. If you actually want to focus out and see the entire moon, you probably want to go to a very low magnification. What is a refractor? What's a reflector? What are optical telescopes and where are they best located? What's the name of a telescope that uses a lens or a mirror to gather light? And what advantage does the Hubble telescope have over regular ground-based telescopes? Refracting telescope is one that actually uses a lens. If you take a look, we have sort of a cannon-shaped object with an eyepiece. That's going to be your magnifier if you put your eye right there. What this is supposed to do is collect the solar radiation equal to the front of this cannon, use a lens to bend them together, and then focus them into your eye. So you're making the iris of your eye as big as the front of your telescope. Collects lots of radiation, and you can see an advantage. If you've ever used binoculars to look at the moon, you're taking something that's very easy to see with your eye, and it may actually even get to a point where you are squinting because there's so much light. The other main type of optical telescope is the reflector. Refractor bends or refracts light. Reflector collects by reflecting the light. It uses a mirror. It's a lot easier to create a perfectly aligned and developed mirror surface than it is to create the entire 3D lens. If you have bubbles or particles or something in here, it's going to bend that light different than what you want, and some will get focused to the actual cannon. Some will not even really make it through the lens. That mirror, you can put anything you want on the back, as long as that one little surface is highly reflective. And what it does, again, it's a cannon. It's opened up in the front. Light comes in, hits this concave mirror. It bends it back. It reflects it back, but it reflects it at an angle. It goes into another mirror, which can bend it even more. And then there's an eyepiece. You wouldn't want to actually put your eye right there because your head would block a lot of the incoming solar radiation. But again, it's making the opening of your eye the size of the front of the telescope. It is to collect the light and then focus it so you can see it. The magnifier may be put into the eyepiece where you can magnify the image if you wish. The best place to actually put an optical telescope is as far away from artificial light. If you ever try to look at stars looking in your backyard, it's probably better in your backyard than your front yard because of street lights, although your neighbors in the back may actually have a well-lit backyard. But you want to get as far away from artificial light as you can. You also want to get as high as you can. Cloud cover causes problems. Weather with the cloud cover can cause problems, or just the movement of air, which picks up sediment, particular material, will cause problems. Both of these things are limited to only being able to use really well at night and only in good weather where we don't have the clouds. This is for sure the Keck telescope. Give you some idea of the size. You can see some vehicles that are parked down here below. It's put way high. You can see those nice white puffy cumulus clouds, which are usually over your head. Most of the time they are down below this mountaintop. The mountaintop does get snow, so there are clouds that do form above it, but not near as much as there are down below. But this is a Keck telescope. These two, I think, have like 17 or 18 or 20-foot mirrors inside. They can be turned to point to the same part of the sky to basically give you an eye that would be as big as drawing one mirror that's the size of this. These mirrors are actually honeycombed. They're hexagonal, smaller mirrors that are put together to make this larger one. Makes it much cheaper to do so, and you can also do some fine-tuning by bending these things. If we get some attenuation, in other words, the twinkling of stars, we can actually sometimes bend these individual mirrors a little bit to minimize that twinkling. It gets us a much more clear image. Why is the Hubble Space Telescope, HST, so much better? Well, think of a mountain that's 190 miles tall. It's in night all the time. Even in daytime, which you can see below, it's dark enough here to view. You can view this thing 24/7 every single day of the year. It's been up there for many years. It does have a 3 meter reflector back here, so the light actually opens up. They can close it if there's a large amount of solar radiation coming to protect the electronics that are in there, somewhat protect them. But the light goes in, hits the 3 meter lens, and then bounces back up. It's collected and it can be beamed back down using radio waves down to the Earth. We can also send messages up to this telescope telling it which way to turn, how long to stay in a particular position. It does have some more electronics on there to do other things, but its main purpose is to collect visible light. This is the Space Web Webb Space Telescope, the JWST. It's not supposed to be covered, but it's going to look like this. Again, I think it goes up in either 2014, 2015. You can sort of see the hexagonal individual mirrors. Again, it's a lot cheaper to put these together than to create a mirror that's this size. I think it's supposed to be twice the size in every direction, so 4 times the collecting ability of the Hubble Space Telescope. So it is going to see a lot more clear image. The resolution is going to be a lot better, and it should actually be able to see farther. Hubble can almost see to what we think is the beginning of the universe, 14 billion light years away. This one should actually bring it in a lot more clear. What are the forms of the electromagnetic radiation, and how are they the same? How are they differ? Here's an electromagnetic spectrum again. If you take a look at it, we got the radio, microwave, infrared, visible, ultraviolet, X-rays, and gamma rays. We have the wavelengths going through, one similarity. We have the speed of light going through, same similarity, and what's different is the wavelength. And you can see they get much higher. If this was sound, we would call these high pitch, and these would be low pitch. With light, these are high energy, this is low energy. This gives you a little bit about the size. These guys are planetary size or building size. These waves get to be about the size of a human. So when we're talking about radio and microwaves, we're still talking waves that are 6 feet between crest to crest. When we get microwave into infrared, we're talking honeybee, point of a needle. Get into visible, they're the size of protozoan, which is why optical microscopes have a tough time seeing some of these things because they're smaller than the wavelength of light that bounces back to your eye. Ultraviolet, the size of molecules, which make up protozoan. Get into X-rays, they're the size of atoms, which make up the molecules. Get into gamma rays, we're actually talking about atomic nuclei size and even smaller. Gamma rays can go through an entire atom or a whole room of atoms, missing all the electrons, all the protons, all the neutrons. Problem is when they get into molecules and they get into an atom and they actually change the atom shape, or they knock off parts of the atom, which can change the molecule. The absolute probably best thing it can do is to kill the cell. We don't want to kill too many of them. Excuse me. The absolute worst thing it can do is to cause damage to the cell and make it actually get through its mitotic cycle and get to a point where it doesn't know when to stop, where it can actually make a part of your liver much larger than it's supposed to be by creating too many cells. We call that cancer, which actually makes your liver not able to do the filtering of the blood, or you make the lung not able to breathe, you make the brain not able to send or receive messages. Cancer is a really scary thing. High energy waves tend to actually be much more damaging than lower energy. Okay, frequency. You can take a look at these. Frequency looks like 10 to the 4th. It sounds pretty big, but notice what happens. We get 10 to the 8th, 10 to the 12th, 10 to the 20th. They actually get more and more waves. They get higher and higher energy as we go. You can see Roy, again, infrared more red, violet more violet. Roy G. Biv going in this direction. Temperature of the emitting bodies. If we have stars that actually have a relatively low temperature, 1K, almost absolute zero, they're going to be producing radio waves and probably not much else. We get to stars that are located around 10,000 K. Our sun is about right in here. They actually start producing different wavelengths. Some stars are capable of producing multiple forms. Really hot stars probably just in this form. Really cold stars probably in here. The middle stars can maybe produce a myriad of these things. You know our sun produces visible light. You know it produces infrared. If you ever walk out from under a tree in a hot summer day and you feel the sun intensity, it produces lots of heat. We know it produces ultraviolet. It does produce X-rays. It does produce microwaves and radio waves and gamma waves. It produces all of these. This is wavelength. We talk about millimeters as being these small little lines on a meter stick, centimeters being these things. The whole meter would be when we talk about 100 of these. Right about here, this is, we're talking about, I think, centimeters. Actually, these are meters. This is 1,000 meters, so 1,000 of these things. This is 1/100th of a meter, which would be that distance. This is 1/10,000th of a meter. Taking this thing and dividing it up into 1,000 pieces, very small, and they get even smaller than that. From small to large, going from this end that way, gamma rays, X-rays, ultraviolet, visible, infrared, microwaves, radio waves, and actually starts off with FM, frequency modulated and then the larger AM radio waves, amplitude modulated, and then actually even longer radio waves going off in that direction. They all travel through space in waves. They all have crests and troughs and wavelengths and wave periods. They all travel at the speed of light, 186,000 miles per second. The only way they differ is in wavelength. How many waves would pass a particular location at a certain time, which is the period. Wavelength is actually measuring the distance in terms of meters or centimeters or parts of. How do radio telescopes work? Again, they're very much like a reflector. Light comes in, they're reflected back up. We have telescopes for every conceivable wavelength. This is a X-ray telescope. This is the Chandra, which is actually up in space already collecting and looking at things through the X-ray images. This is supposed to be a gamma ray instrument. Looks very much like a reflector, and you can see individual plates that are pointing in different directions, but supposedly this can collect those itty-bitty, teeny-tiny, itsy-bitsy waves, and again do the same thing, send it up to a place where it can be collected and then sent to wherever it needs to be sent. There are lots of things on here. Counterweights. This telescope, because it can be huge, weighs has a lot of weight, a lot of mass. We put a counterweight on it so we can actually work on this moving this thing around back and forth. This is a rainbow. The rainbow actually works with colors of the spectrum. Goes from red to blue. When we actually can pass light through a prism, we can get that same sort of thing. You know that light's made up of Roy-G-Biv, visible light. A prism breaks it down, cuts the white light into its individual areas. You have a Java applet down here, which I'm not going to go to. You can, if I mouse over it, it's how stuff works. But you can actually see something about this whole thing. Prism is a triangular piece of glass. Showed this to you before. White light goes in, and because it actually hits at an angle, this wheel, if you think about this as being a car, a tire on this side and a tire on this side, the tire on the lower side hits first, and because of that, the car bends in that direction. It starts bending the colors, the wavelengths into different areas, so it starts breaking up. It starts breaking up the light into its individual colors. You can see Roy-G-Biv. Appearance of these colors is caused by refractive index. Each of these things have a different refractive index, so they actually bend the colors in different directions. The angle which it's bent is dependent on its wavelength, and this is why we can break the red light away from all the other colors. This is how a rainbow actually works. You need a sun. So it has to be sunny behind you. You're looking toward the raindrop falls, the light enters the raindrop. It actually acts like a prism because of that angle. It refracts the light, it hits the other side, bends it back, and separates it into the purple to red views. This raindrop does the same thing. If you had another raindrop down here, it would actually be too low, and the rainbow would be below you. Happened up here, would be too much, or the angle would be too high, and it would be above you. Here's an actual picture of a rainbow. You can see it's sunny. You can also see it's cloudy. You can see the rain band, but the light's coming in, hitting the raindrops, and then bouncing over. And actually, we're in an airplane taking this picture. I did not take this picture, but we would be in the airplane taking this, and the angle would be perfect for the observer in the airplane. I'm sure they could probably see a rainbow, but they would see it farther in. You can see some of these things are farther back, and we can see a rainbow in the back, but if you take a look at that rainbow, this is like the opposite of Roy-G-Biv. This one actually is Roy-G-Biv, another part of the optical illusion. What can astronomers learn from the stars from their spectra? When astronomers pass light from a star through a telescope that has a spectrometer, the difference between a spectroscope, which sees the spectra, and a spectrometer, which measures, all this does is tell you what wavelength is what. We will be using spectrometers. The spectrometer actually sees the sunlight, breaks it up into the individual colors of the spectrum, the colors of the rainbow, except that there usually are going to be dark lines in it. When we took a look at a spectroscope or a spectrometer inside of our classroom, and we looked at different emission tubes, we're going to see emission spectra. We can do that with stars, we can do it with the sun. This is the spectra from our sun. You can see lots of different lines. We've actually located or seen every element we can see on this planet on the sun. Some of these materials, like hydrogen and helium, tend to make up most of the mass of the sun, but it does have other elements inside of it. All of them causing the individual lines that you can see on here. Some of these lines would code for the hydrogen, some would code for the helium, but not all these are hydrogen, not all these are helium. So what's going on when we actually see these spectra? Turns out that every element sends out a particular frequency of light, a particular color of light. And the element is passing through space. It passes through a very cool part of the atmosphere of the star, and then it actually is absorbed by the atmosphere elements, and it produces these colored lines. And it actually does so very well, and it's called the fingerprint, because each element has a different fingerprint or a different setup of these individual spectral lines. Let's see if we can figure out the composition of a star. Here's a spectra of 4 elements: calcium, hydrogen, iron, and magnesium. Notice that calcium has a lot of spectral lines, hydrogen only has a few, iron has somewhere in between, magnesium has less. But also notice where these lines are located. This line is actually very strong in this light blue area. This particular element doesn't have that line. Same as this line over in the red. This particular element doesn't have that particular red, even though it's got some other lines that are red. And iron, all these lines belong to iron. So all these lines that are iron have to be in the star in order for iron to be in there. All the lines for hydrogen or calcium or magnesium have to be in there. If some of these lines are in and some of them aren't, calcium's not in the star. If that line is and this line isn't, hydrogen isn't in the star. If those lines and that line is in there, but these aren't, iron's not in that star. And if those lines aren't in it, magnesium isn't in the star. Okay, so here's the spectra of a mystery star. If you take a look at it, do you see calcium in this star? Well, I don't see these lines at all, so I would say calcium's not in this star. Is hydrogen in this star? This line may or may not be. This line is not. Hydrogen is not in the star. Is iron in the star? Do you see these lines? Do you see these lines? Do you see those lines? If you do, iron is in the star. Do you see that line right there? And do you actually see that there are other lines in there? So this star has got other elements that aren't one of these 4, but I would say that iron and magnesium is in this star. So which elements are present? Is calcium? No. Hydrogen? No. Iron? Yes. Magnesium? Yes. You're correct. The star has 2 elements that are present in those 4. Iron and magnesium. It does have another element in there. I just can't tell what it may be. Okay, what are the 3 different types of spectra? Continuous color, Roy G. Biv all the way across. Emission, black background with lighter colors, but the colors are in the right location. You can see this is the red end, this is the blue end. Absorption, looks like it wants to be continuous, but now it has dark lines. But notice the lines in the emission and the lines of the absorption are in the same location. Emission, these are coming from like a hot gas nebula, which we put through our spectrometer to get this. Absorption, the light's being produced here, it's being absorbed by this, and it's actually showing us the elements that are inside this this nebula, which would absorb the light that actually gives us the black lines in the color. Continuous spectra, light like you'd see in a rainbow, Roy G. Biv. Absorption spectra, dark lines actually on a colored background. Emission spectra, colored lines on a darker background. The way it's created, you get a light source in the background. If you can see that light source, you get a continuous spectrum. If that light goes through a nebula, and that nebula absorbs, like if hydrogen light goes through there, and neon light goes through there, and argon gas goes through there, but this thing is only made out of hydrogen, it's going to pull out the hydrogen light, it'll absorb it, and we'll see the absorption lines. Or if the nebula is able to produce its own light, we get what's called an emission line. Again, we get dark lines on a colored background, we get colored lines on a dark background. Those are the difference between the two. They're caused by looking at stars through different materials. Here's an animation that sends out the colors Roy G. Biv. They go over to this particular material, and this material absorbs the orange light. And we get, basically we don't get the light, we get an absorption spectra. You see that the orange light gets bent back out of this object, and we get what's called the emission. So if it emits light, we see it as emission, and if it absorbs the light, we see it as an absorption. Emission have the dark line, the colored lines on a dark background. Absorption has the dark lines. Let's do it on this side since we can see it. Emission has the colored lines on a dark background. They have a white background on this one. Absorption has the dark lines on a colored background, like they're showing right there. How do we identify elements? Well, we're going to do a lab where I'm going to give you spectra of different elements. They will not be colored, they'll just be lines. But if you take a look at these, and if I mouse over it, actually I don't have to mouse over it, you can see it. If you type that web address in, you can actually click, I think, a periodic table and actually see lots of different spectra of all the different elements. We have these elements, we can make a neon light, we can look at it, we can make a carbon light, we can make a lithium light, we can make a hydrogen light, and we can actually see the lines that it produces. How does spectra give us an idea of the characteristics of a star? Wouldn't it be kind of cool to know about a star without us ever getting there, since we probably never will get there? Certainly not us that are in this room right now. Other than chemical composition, with a fingerprint, spectra can tell us some other things. They can tell us which way the star is moving. They can tell us relative temperature. Hotter stars than normal spectra look different than cooler stars than normal, or normal stars. If they're actually under more pressure, they tend to be hotter, so they actually are showing that. If they're under less pressure, they tend to be cooler. It's sort of like the three little bears, too hot, too cold, just right. So we're going to be doing a spectral analysis lab. I'm going to give you guys spectra of known elements. It actually shows you wavelength in terms of distance, in terms of angstroms. It also shows you in terms of color. So you can see neon light is here. Neon is pretty strong in the red, but also in the blue. And if you ever look at neon light, it has that kind of orangish color. Mercury's more yellow because the colored spectral lines are in yellow. Argon would be more purple because most of the lines are up in purple. Helium tends to look sort of white because the colors are pretty there. Hydrogen looks pretty white. Sodium, guess what color sodium is? And you can see that sodium is actually, that sodium colored lines are in all of them. Very definitely a yellow color. And then calcium is going to look different, iron's going to look different. And if you look at all these, they're going to look different to our eyes, and they look different because of the spectra that are in there. I'm going to give you 4 fictitious stars with unknown elements: star A, star B, star C, and star D. And you're going to actually take this star and you're going to slide it across using that little sodium doublet that's right there as a reference point. You're going to slide these across and you're going to say, are these lines in this star? If yes, iron's in that star. Are these lines in there? If all those lines are there, it's in that star. If this one's in there, we're going to use that for its sliding, it's in there. If that's in there, it's going to work. If that line right there is not in that star, no helium is there. If that section's not in that star, it doesn't have argon. If that's not in there, we don't have mercury. If those lines right there aren't there and everything else is, we don't have neon. But we're going to try to figure out what the stars are. And then if we actually look at these 3 stars, if you notice, that line is pretty much in the same location. If you take a look at these 2 lines right here, these lines all seem to be shifted. If this is the control, all seem to be shifted a little farther down. And because of that, we can look at this chart up here and see that it's shifted from a very small wavelength to a much larger wavelength. Maybe not too much larger, but it's shifted more toward the red end. That tells us this star is moving. Notice these lines are larger. They're brighter than normal. How would you make the light brighter? This star's probably got a different pressure or a different temperature than star B, even though some other things may be the same. Doppler effect. Doppler effect is, again, the apparent change in wavelength due to motion. If it's moving towards you, the waves get kind of smudged together. If it's moving away from you, they get pulled apart. If it wasn't moving at all, we would see waves on the same side being the same distance. They would be normal. We could tell that that thing has no relative motion to us. So either it's not moving or it's moving in the same direction at the same speed we are. Doppler effect is a change in frequency or wavelength of a wave. It's caused by the change in distance between an object that's creating the wave, which is the cause of the transmitter, or the person who's measuring it, or the watcher, the listener, or the receiver, and what they see or what they hear in terms of the wave. Here is a car with its engine, and as it's moving, you can see it actually, if it's not moving, you can see the waves are the same. As it does move, the waves get crammed together. As it moves away, it gets different. If I go beep, 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 so you can see the difference in frequency just based on those waves. Another word for causer is sender. Another word is the change in direction is going to be the speed of the object. Sound of that the driver hears. If this car has got its horn on, let's say, the horn for the driver sounds the same all the way because the horn's moving at the same speed, the same direction as the car. Observer that's down the street, the car's moving, we're going to hear that horn as being a higher pitched horn. The wavelengths are closer together, and if you remember, that's more of a violet or a blue shift. And observer where the car's up the street, where we're actually going to where the car's going to be moving away, we're going to actually hear that thing as a much lower pitched tune, much more red if we're talking about color. If you actually go to this site, you can see more about this as a flash tool. What are red stars? Shifted stars, what do they mean? What are blue shifted stars? What do they mean? If a watcher and causer get closer, the wavelength is shorter and the frequency is higher. If this is light, we call it a blue shift. If it's sound, we call it a higher pitch. If you see this star was there, and now there, the wavelength gets moved closer together. Now, you can't really see what the wavelength was supposed to be, but you know from other things that I've shown you, these waves are closer together than they should be. For sound, we call that a higher pitch. The distance between the watcher and the causer gets longer, the frequency is going to get lower. We call this wavelength increasing. We call that a redshift, and if this was sound, we would call it a lower pitch. But if you take a look, now the star was there, then there, and now there, the wavelength actually is much lower. They would see it as more red. Here are 3 galactic images. If you take a look at these as being the Earth and these are the galaxies, you can see one's moving away and one's moving toward. This is what the line is supposed to look like, sort of between the the green and the yellow. This one that's actually moving this direction looks like it's shifted more towards the yellow end. We call that a red shift. Even though it doesn't turn red, it is more red than what it was. This galaxy is moving away. This one's actually now solidly in the green, where again it was between the yellow and the green, maybe in the light green area. Now it's very obviously in the green. It is not in the blue area, but it's been shifted more blue than what it is supposed to be. So a red shift, more red than it's supposed to be, we know the thing is moving. In fact, if this had shifted more toward the orange, we know that it's moving away even faster. If this is shifted from there even to the light blue, we know this one is coming toward us. And we do know that the Andromeda galaxy is moving toward us because it is slightly blue shifted. And almost everything else in the universe is red shifted, showing us some idea of this big bang where material is being thrown out in all directions. The only explanation of being red shifted in all directions is that there was an explosion and we're all now moving away. Okay, that's the end of the show. Hope you enjoyed it. Hope it answered some questions. Get busy on that review. This quiz should be pretty simple if you understand the things that are on there. Thank you much. Appreciate it. Bye.